Hey Phys 1 kids, Campbell here. In this video on angular kinematics, we're going to talk about how we talk about position, velocity, and acceleration when we're rotating. Now in class, I've said that every linear variable has an angular variable, and that's true from a kinematic standpoint too. When we talk about position, when we're talking about translational motion, we're talking about x or the change in x. But when we're rotating, we talk about it in terms of the angular theta. And the velocity v becomes the Greek letter omega, and the acceleration a becomes alpha. So we now switch to some Greek letters, which make it even more fun when we're rotating. Now let's first talk about angular position. So when an object is rotating, or just a particle on a string that's going in a circle, or a disk that's spinning, or a wheel that's turning, if we take a look at just one particle as it rotates, we measure the angular position with regard to the x-axis. And we have to have a positive or negative, just like in kinematics, right? Positives or negatives are about direction. When we're moving counterclockwise, right, counterclockwise, that's going to be considered the positive direction, just like a counterclockwise rotation is positive torque. Now, when we do angular positions, we use the unit radians, which we abbreviate rad. We don't use degrees, although there's going to be some problems I'm going to have you do where you're going to convert between the two. We also talk about not just the angular position, but the arc length. The arc length, s, is the actual distance that the particle is traveling along its circular path. And there's some relationships between that theta in radians and arc length, which is a distance. That theta is equal to the arc length divided by the radius, or more commonly we use it like this, that the arc length, that path that we're traveling, is the radius times that angular position in radians. Now, just a couple conversions that are important for you. If we think about one revolution around a circle, right, the circumference of the circle is 2 pi r, right? So that would be the arc length s. And so anytime we go in a full circle, we have traveled 2 pi radians, right? If we take our 2 pi over r and divide by r, right, our arc length divided by our radius, we get 2 pi radians. So that means if I travel halfway around a circle, I've traveled pi radians. So one revolution is equal to 2 pi radians, which is equal to 360 degrees. Now, what about angular velocity? Angular velocity is the angular displacement per time that particle moves. So remember that our linear tangential velocity is position over time, the change in position over change in time. Our angular velocity is the angular position change over time. So if we calculate the angular velocity in these two different scenarios, remember that angular velocity is the change in the angular position over the change in time. Now, in this case, if you remember that a whole circle is 2 pi radians, that means a half a circle is pi, which means that if I go 90 degrees, right, or a quarter of a circle, I'm at pi over 2. So in this case, my angular velocity is pi over 2 divided by the time, which is 5 seconds, which of course is then pi over 10 radians per second. And in my second scenario here, I've traveled half a revolution in 5 seconds. So my angular velocity is going to be pi over 5, and the units are radians per second. Not so bad, right? Now, a couple things about period, right? Remember when we talked about uniform circular motion, we talked about the speed. Remember this equation, velocity is 2 pi r over t. We use that in, that's a big T, uniform circular motion, right? Because the period is the time to go around a circle once. And in linear velocity, we were talking about that distance, 2 pi r. Well, when we deal with angular velocity in terms of period, remember one revolution in radians is 2 pi. So 2 pi over t is the angular velocity or angular speed. Remember again that frequency, which is revolutions per second, is the inverse of a period. Now, one of the really cool things about angular velocity is that every point on a disk, a solid object, a rigid object, is moving with the same angular velocity. It's sweeping out that same angle as every other point it's aligned with in the same unit time. So what's really cool about using angular measurements is that it doesn't matter where you are on the disk, whether I'm here at point A or I'm here at point B, their angular velocities are the same. However, the linear velocities, right, are not the same, because the linear velocities, right, are a function of the distance from that center point of rotation. And in fact, if you compare this equation to this equation, you'll notice the one difference, r. Remember that was one thing I talked about in class, how angular and linear variables are very similar to each other, but the difference is r. Well, once again, our linear velocity, or the tangential velocity we call it, is equal to that angular velocity times r. Remember acceleration, right, was alpha, the angular acceleration, times r. We talked about that in our last video. So r is always involved when we're going between linear and angular variables. Let's do a calculation. So our car engine, the crankshaft turns at 3,000 RPM. What's the shaft's angular speed? Well, angular speed, right, the units for angular speed are radians per second. What I have here is 3,000 revolutions per minute. Well, first of all, I need to get out of the minutes and get to seconds. So there's, in every 1 minute, right, there are 60 seconds. And so that gets us out of minutes. But I don't want to be in revolutions per second. I want to be in radians per second. So remember that 1 revolution is equal to 2 pi radians. So that gets me out of that. So 3,000 times 2 pi divided by 60 is going to give me 100 pi radians per second. Angular velocity. So make sure you can convert between revolutions per minute and radians per second, because you usually get stuff in revolutions per minute or revolutions per second. Angular acceleration, just like in kinematics, acceleration is the change in velocity over change in time. Well, the same is true for angular acceleration. Angular acceleration is the change in that angular velocity, omega, over time. Now, as I said in class, the units of angular acceleration are radians per second squared. Now, we only have angular acceleration if angular velocity is changing. If our angular velocity is constant, right, then I'm in uniform circular motion and I don't have any angular acceleration. Of course, there are signs of angular acceleration. Remember in linear motion, we talked about how if you had a positive acceleration, you were speeding up in the positive direction or slowing down in the negative. Remember, we went through that whole plus, 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 minus scenario to come up with our signs of acceleration. Well, the same is true for angular acceleration. What I like to do is think about, I call rotating clockwise the positive direction, right? That's the positive direction. I call speeding up positive. So if I am rotating counterclockwise, that's a positive. Speeding up is a positive, so that makes my acceleration positive. Or here I'm rotating clockwise, right? That's the negative direction, and I'm slowing down, and I know a negative times a negative is a positive. So again, if I'm rotating clockwise, the negative direction, and I'm slowing down, that's positive acceleration. Angular acceleration in this case. Down here, if I'm rotating in the positive direction, my counterclockwise direction, but I'm slowing down, a positive times a negative gives me a negative angular acceleration. And my other case here, rotating clockwise in the negative direction, but speeding up, again, positive times a negative gives me a negative angular acceleration. So I don't remember necessarily speeding up and slowing down and what's what for positives and negatives for acceleration, just like with linear acceleration, the same for angular acceleration. I like to think of it in terms of pluses and minuses. It makes it easier to remember. All right, let's talk some more about acceleration in circles. You're probably wondering, how is this different from what we did in our last unit when we talked about uniform circular motion and centripetal acceleration? Well, any object, no matter how it's rotating, if it's speeding up or slowing down and going at constant speed, always has centripetal acceleration, which always points towards the center of the circle. When I'm in uniform circular motion, right, which is really the focus of our last unit, the speed was constant, but the direction was changing. And so I have this centripetal acceleration equation, which is v squared over r. So this is the same equation we had in our last unit. I just put that tangential, that t there, just to signify we're talking about that tangential velocity. That velocity is 2 pi r over t, that velocity, the tangential velocity. So still have centripetal acceleration as v squared over r. And in fact, we can relate that to our angular velocity equation, right? If the velocity, right, velocity is the angular velocity times r, I can take that quantity and put it in here, and I end up with this, so that the centripetal acceleration is also equal to the angular velocity squared times r. Now, the reason why I give you this equation is because sometimes you'll be working with angular quantities, and I'll ask you to calculate the centripetal acceleration. Well, there's no need to go back and calculate the linear velocity. No need to say, okay, I know the angular velocity, so if I times that by r, I can get v, and then I plug it in here. You can actually just use this equation here if you remember it. If not, you can always, use our equations from before to get there. Now, how is uniform circular motion and centripetal acceleration and angular acceleration related to each other? Like, what is going on? Well, if I have no torque, right, no net torque, and an object is rotating, it's going to rotate in uniform circular motion. So I'm going to have constant speed around my circle. But if there is a net torque, then my object is going to have acceleration, right? We said that the angular acceleration is equal to the net torque divided by the rotational inertia. And so if I have a net torque, my object's going to speed up or it's going to slow down. So its angular velocity, its tangential velocity is going to change. Now, in this case here, if you look at this picture, notice these green arrows are my velocity, my tangential velocity here. And you can see that those arrows are getting bigger, which means this wheel is speeding up. Now, as it speeds up, also notice that the centripetal acceleration vectors are also getting bigger, because remember that centripetal acceleration is v squared over r. So if that tangential velocity goes up, then that centripetal acceleration goes up. But at a constant torque, right, if this value is constant, then that value is constant. So, and that means, and remember we have this equation, right, that the tangential acceleration, not the centripetal, but the tangential acceleration is equal to alpha r. So if this is constant, because this is constant, then this is constant. And that's why when you look at this picture here, these arrows, my tangential acceleration arrows, are not changing. I'm speeding up because I have a net torque. Just like I'm speeding up, if I have a net force, I accelerate. That's Newton's second law. So, but that doesn't mean that I have something different than my centripetal acceleration. Centripetal acceleration always exists if I'm moving in a circle. But if I'm speeding up, then I also have a tangential component. Now, let's just talk a little bit more about tangential and centripetal accelerations. Tangential acceleration is always perpendicular to centripetal acceleration, because centripetal acceleration, right, always points towards the center of a circle. So a tangential acceleration is always tangent to the circle, so those are always going to be perpendicular to each other. Both can happen at the same time. If an object is rotating and speeding up or slowing down, then I'm going to have tangential and centripetal acceleration. Anytime I'm rotating, I have centripetal. Anytime I'm changing my velocity, I have tangential. So the tangential component is only there when there's changing speed. So when there's changing speed, I have angular acceleration and I have linear or tangential acceleration. That centripetal component is due to the fact that the object is changing direction. So the centripetal acceleration points towards the center of the circle, and it's due to the fact that the object is changing direction. Clear? Not so clear? Did I have you at AP Phys Kids? No. So that tangential acceleration, that tangential component of the acceleration is due to the changing speed. If there's no changing speed, so if I don't have any changing angular velocity or changing linear tangential velocity, I don't have any tangential acceleration. The centripetal acceleration component is always there. It's because that is due to the changing direction. In order to rotate, you got to change directions. So tangential may or may not be there. If I'm in uniform circular motion, it's not. But the centripetal component is always there. All right, last thing is, remember the kinematic equations. My favorite, my least favorite, the one that I could care less about. Well, we have the same thing for linear. They just are for rotational, but they look ugly because they have those Greek letters in them. So I want you to put these down. Our translational ones, right? My favorite one, final velocity is equal to initial velocity plus acceleration times time. Instead of the v's, we put in our omegas. Final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. And my least favorite equation, final position equals initial position plus initial velocity time plus 1/2 at squared, is now the final angular position is equal to the initial angular position in radians plus angular velocity plus time, or time, plus 1/2 angular acceleration times squared. And then here's my indifferent one. The angular velocity squared, final, is equal to the initial angular velocity squared plus 2 times the angular acceleration times the change in angular position. So write those down. We're going to work on some practice problems in class with these. So fill out your WSQ, answer the question, and I'll see you in class.